Prateek Bansal. I'm an assistant professor in National University of Singapore. And we are going to have two parts of the lectures. In the first part of the lecture, I'm going to talk about system level work, which is more of a transport planning at a system level. How do we use the different type of data sets which are coming in? I think you might want to stop the noise. I think everyone is asking. Is it okay now?
Yes.
Finish? Okay. Sounds good. Okay. So I'm going to talk about the two parts. The first part is more system level, which is more of how do we do the transport planning when you have now more emerging data sets, like transit smart card data set, you have a cellular data set, you have credit card transaction data sets. How do you use all this in transport planning and where we are really heading, right? So I'll first set up the foundation and then I'll talk about some of the work that we are doing and we'll try to motivate that. I'll take around 50 to 60 minutes talking about that. Then I got to know that I'm the only one who is talking today. So I have luxury to extend this little bit, I guess. So we'll take maybe 10 to 15 minutes break, and then we will take 1 more hour where I'll more talk about new models in cognitive psychology which have been emerging, and they can be alternative to the discrete choice models that we have been using in transportation from maybe past 40 years, right? So it's a very different perspective. First one is more system level, and second one is more individual level. So let's get started. So what I'm going to talk about today is a joint work with Koa Vo, who is a research fellow in my group, Seng Wu, who is a research fellow again in my group, who is a graduate from Seoul National University, Swapnil Mishra, who is in epidemiology department, or I would say public health broadly speaking, but he does a lot of work in epidemiology. So all the work that we do in using these emerging data sets is also useful in epidemiology, right? So that's why we are also working with epidemiologists, bringing mobility and health together. And this work I'll briefly mention how does the mobility connect with the health. Then Paolo Senti, who is from MIT Sensible Cities Lab, who has also contributed to what I'm going to talk about. So let's get started with the topic. So I assume that you are familiar with the activity-based model. And if you broadly think about the activity-based model, the idea of the activity-based model is you have to first generate a synthetic population. Basically, if a city has 6 million population, then in the computer, you want to generate 6 million agents who have similar demographic and the home and work location distribution as you have in the population, right? That's what we mean by synthetic population. And the second part of the activity-based model is generating the activity schedules of synthetic population, right? So the first part is generating the synthetic population and second is the activity schedule, right? I would say these type of models have started becoming more popular in early 2000 because the computational power started increasing and we have moved toward the agent-based models. So this is the era of activity-based models. I can tell you that even now the agencies, the government agencies are moving toward activity-based models who have been using the 4-step model for a very long time. So it's now no longer just a research topic, it's happening in practice as well. So if you broadly see what do we do generally when we create the activity-based models, we use the household travel survey data. What do we do in household travel survey data? We collect the 1 to 3% of the population's daily activity schedules and demographic characteristics. And we try to use their data to generate the synthetic population and create the activity schedules of that synthetic population, right? But there are two main limitations of household travel survey data set. The first one is because it's a 1 to 3% of the population, it has very low spatiotemporal heterogeneity, right? And I'll talk about this, like what exactly this issue of the low spatiotemporal heterogeneity. The second aspect is the low frequency of data collection. Generally speaking, household travel survey data is collected every 4 years, right? But your patterns, your mobility patterns change more frequently, right? Especially if pandemic type of situations happen, then you need to really update your mobility patterns more frequently. But household travel survey doesn't allow it. It's very expensive to do it more frequently, right? So we have to think about what are the potential ways to address these two issues in the household travel survey data set, okay, first thing. But before getting into that, let's first try to understand the first issue more clearly. What exactly is this issue of the low spatiotemporal heterogeneity? So if we look at the issue of the low spatiotemporal heterogeneity, let's try to understand this from an example. Let's say there is a population and there are 3 zones in the city, A, B, and C. And we have a population level distribution of the people departing from one zone to another zone before 9 a.m. and after 9 a.m. We call them origin destination matrices, right? And if you look at the sample, let's say you take the sample from the population, you would see that there are many zeros that you would observe. What that means is you observe some attribute combinations in the population, but you don't observe them in the sample, right? And that's a problem because if you create any model using the sample data, you have these missing data, right? So what are the 2 potential ways that we can address this? So the first approach is to expand the sampling distribution, even if we don't observe the population level distribution. What does that mean? So let's say the red circle is the population distribution, and what you observe is the sample distribution. This figure is in the attribute space, right? So it's an attribute space. Certainly the population level distribution will be quite bigger, and the sample level distribution will be a bit smaller. So all the generative modeling that we try to work with, I would say that even the discrete choice models are also generative models because you are trying to generate some probabilistically out of the sample, right? So all you are trying to do is you are trying to expand your blue circle to the black circle. You want to expand your attribute combinations that you don't observe in the sample, right? But the issue is when you try to expand your blue circle to the black circle, almost all generative models, I wouldn't say almost all generative models have this problem that your black circle, the generated one, pictorially have something like this scenario. What does that mean? You will be generating some attribute combinations which are not even in the population circle, which we call them structural zeros. Then you have, you are able to generate some of the combinations beyond what you observed in the sample, but that are in the population. So you have sampling zeros and you have structural zeros. So the idea is, what are structural zeros? If you think about from a population synthetist perspective, the structural zeros is like children's having full-time job, right? So if you're generating these type of synthetic agents, those are structural zeros because they do not have in the population, right? So they don't exist in the population. So the problem is, how do you reduce these structural zeros? I'm sure we cannot eliminate them, but how do you reduce these structural zeros but increase the sampling zeros? Because we want to go from sample to the population, so we want to increase the sampling zeros but reduce the structural zeros. Some of the work that we did on how do you increase the sampling zeros and reduce the structural zeros can be found out here. So when the slides are distributed to you, you can look into this further. So this is the one direction we have been spending too much effort in terms of how do we handle these structural zeros and sampling zeros. Some of the work that we have done recently with Eugene and his team recently is how do we use these large language models to reduce the structural zeros? So to broadly speaking, you can combine these generative models with large language models, right? And that can help you reduce the structural zeros and increase the sampling zeros. So to give you a very brief picture of this, because this is not what I'm going to talk about in detail, but something you should know as an emerging direction right now, if you use the deep generative model, any state-of-the-art deep generative model, and then you have the feasibility of 81.4%. What does that mean? You still get around 19% of generated population or generated synthetic population, which is not there in the actual population, right? But if you use the Bayesian networks with LLM, then you are able to reduce those structural zeros to close to 5%, right? Obviously, you sacrifice a little bit on the heterogeneity of the population that you're generating, but this is very promising because when you go to any transport agencies, they want to be very conservative, right? They don't want to create these synthetic population which has agents with so many structural zeros, right? So there is a potential, there is a value in using LLMs, but the field, moving forward in terms of how do you combine LLMs with the statistical models, right? And we are trying to work toward this direction more. So this is, I would say, is the first direction, that how do you increase the structural zeros, reduce the structural zeros, and increase the sampling zeros. So that's the direction where the field is moving. The next direction that we are going to focus on today more is the data fusion. Now you have more of passively collected data set which have high spatiotemporal heterogeneity in the data, right? And how do you leverage that high spatiotemporal heterogeneity to address that zero cell problem? And at the same time, because this data is collected more often, so you can update your synthetic population and activity schedules more often because you can get this data more in the real time, right? So this is a second direction to address the zero cell problem and the issue of not being able to update the synthetic population and activity schedule more regularly, right? So if we look at more specifically that what are the major differences in traditional household travel survey data set and the passively collected data sets. By the way, the example that you have here is from Seoul. This is the smart card data and this is the household travel survey data. So you can see the sparsity of the data sets that you have from the smart card data compared to the household travel survey data. So the major differences, if you look in the household travel survey data and the passively collected data, in the household travel survey data, you have a low spatiotemporal heterogeneity, but in the passively collected data set, you have high spatiotemporal heterogeneity, but lack of information on the activity purpose, travel mode, and the social demographics, right? So there is some complementary information in both data sets, right? We have to find a way that how do you combine these two informations together to utilize, to address these issues of low spatial heterogeneity, and at the same time, the being able to update these patterns in the real time. Okay, so if you think about we have been doing extensively work on this data fusion. But I'll talk about the two new work that we have done in last 4 or 5 months, and which is more about how do you combine the household travel survey data with the smart card data to generate the time-dependent origin-destination matrices. And the second one is how do you combine household travel survey data with these time-dependent OD matrices to generate the activity schedule, which is consistent with the household travel survey data as well as the time-dependent OD matrices that you obtain, right? The first one is very relevant for countries which have the very high transit share. For example, countries like Singapore, Seoul, cities like Singapore, Seoul, London, they all have very high transit share, and they also have the smart card data. So the first approach is very useful. I will show the case of Seoul, but we are able to validate this approach for Singapore as well. I don't have results for Singapore now because we are just procuring the data. So to validate our results. But for the second study, I will talk about both Singapore and Seoul case studies. Okay. Let's get started with the first one. So let's first define the problem. What is the data fusion problem in the first case? So the data fusion problem looks like as follows. So here the source mode is defined as the transit smart card data, right? So transit is our source mode, and we have a very rich time-dependent origin-destination matrices for the transit mode. What does that mean? We know that how many people are going in that specific hour from one place to another place using transit. That's the information we have in almost for the whole population, right? What is your target mode? Target mode can be car, target mode can be walk, target mode can be anything, but for simplicity, in this case, we are using all the non-transit trips as a target mode, but the framework is also applicable if you want to generate the car trips only, okay? Or the OD matrix for the car trips, okay? So the issue is the target mode, the non-transit mode OD matrix that you observe in household travel survey data is super sparse. And the transit OD matrix that you observe in the household travel survey data is super sparse, right? But the good thing is you have this very dense, fully observed transit time-dependent OD matrix in the smart card data. So how do we combine these sparse informations with the full information on the transit data to generate basically the time-dependent OD matrix for the target mode, and then you can combine this target mode OD matrix with the source mode to generate the full time-dependent OD matrix, right? So in that sense, if you are able to do that, what we are saying is to transit agencies, if you have a transit data and the household travel survey data, you don't need anything else. You can generate the whole mobility pattern by just using the data that you have, right? So that's why this is valuable. And what I'm going to talk about the method is very simple, but it's surprising that no one has tried that before. So as I said, as a problem setup, we observe something in household travel survey data, we observe something in smart card data. How do you combine them together to generate the time-dependent OD matrix for non-transit mode, right? And we also observe some population level trip generations, right? Because you have a trip generation rates from the household travel survey data, you can use them and apply them to the census data to generate the trip generation related constraints, that how many trips are generated in a whole day from that zone, right? These are the constraints that you can also use. And the departure time distribution constraints also can be applied in this problem. Okay, so let's now try to solve this problem, that how do we really get the very good estimate of this time-dependent OD matrix of the target mode, which is non-transit trips in this case. So I will formalize some notations. So I will be talking using I for the target mode, W for the OD pair, and K for the time, okay? So I for target mode, W for OD pair, and K for the time. So let's say beta I WK means the mode share, the ratio of the mode share between the target mode I and the source mode for the OD pair W and the time period K. Okay, that's what this beta is. So beta is kind of a noisy estimate of the ratio of the mode share of the target mode and the source mode. Again, remember, target mode is non-transit, source mode is transit in this case. Now, how noisy beta is depends on how many observations you are using to calculate the value of the beta, right? So what do you mean by number of observations? Number of observations I'm denoting with the gamma. How many observations are there in the household travel survey data for the target modes as well as the source mode, which are going from time period K for the OD pair K, right? So what I mean by this, let's say in that time period, for that OD pair, let's say you have only 5 observations. Then the estimate of the beta will be very noisy. But let's say you have 50 observations or 500 observations. Then estimate of this beta for that OD pair in that time period will be relatively more reliable, right? So the gamma determines the reliability of the beta. That's a very important point because we will be using it throughout, okay? What is the other information that you have? Because you have transit smart card data, so you have full information of the source mode's demand for that OD pair in that time period, okay? Because it's a tap-in, tap-out data for transit smart card, so you have a full origin destination matrix for the smart card data. Now, the catch here is this beta IWK is only observed for the handful of origin destination pairs and the time periods. Because household travel survey data cannot cover all origin destination time pairs, right? So that's the sparsity issue. That's the zero cell issue that we talked about, right? So what do we need to do? We have to find a way to estimate the beta IWK, right? If we are able to estimate beta IWK for each OD pair and time period, then we are able to generate the target modes. We are easily able to generate the target modes demand between that OD pair W and K because we know the ratio and we know the demand for the source mode. We just need to multiply that ratio with the source mode demand to get the demand for the target mode, which is non-transit in this case. Okay? So the key part here is we need to find a way to estimate beta for the OD time pairs which are not observed in the household travel survey data set. And when I show you results, you will see that this is observed for only 10 to 15% of the OD pairs. So we need to also show for remaining 85%, right? How do we estimate this beta IWK? Okay. And then you can put some of these constraints of the demand generated from that zone and the demand attracted to that zone and the departure time-based constraints that you can put in here, right? Good. So the problem is set up, and problem boils down to estimating the beta for the OD pair and the time, right? So how do we estimate beta, right? Okay, so as many of you are doing your PhD, I would like you to, the message that I want you to give from here, that you have to think about the methods from the data itself, okay? You cannot, I mean, the most impactful work that you do is when you design the customized methods based on your data. Using off-the-shelf method is fine, but you have to start thinking from the problem from the scratch, that what exactly is the problem that we are trying to solve, okay? So now let's think about how you can estimate beta hat. The most simplest way to estimate beta hat is you can just create any supervised learning model because you observe for 10 to 15% of the OD time pairs, you observe the value of the beta. So, and for them, you observe the land use characteristics and many other characteristics for those OD time pairs. So you can use that information to create, you can create random forest model, you can create whatever model you want, but that's something you can do. But what is the issue? The issue is beta itself is very noisy, right? Beta itself is very noisy. So if beta is noisy, then this whole supervised learning model might not be useful in itself as well. So how do we address this issue? So what we say, because beta is noisy, that means gamma is not enough. The number of observations from that OD time pair is not enough to get the reliable estimate of the beta. So the easiest way to do is, let's start think of clustering the observations. Now you can think of any clustering approach, but let's put some constraint that in each cluster, we at least need maybe, let's say 30 observations, 40 observations, 50 observations before creating a cluster so that we get the reasonable estimate of the beta hat. So to show you the idea here, let's say you have these different OD time pairs, right? And for each of them, let's say you have the value of these ratios, but the number of observations that you have is, let's say, 15, 10, 20, 15, and 20. But let's say you decide that we at least want that each cluster should have 40 observations before we get a reliable estimate of the beta, then you can cluster them in this way. This is just an example, an illustration of the process, right? So you can design such kind of clustering where you can constrain that the gamma, the number of observations in that cluster, should be at least 50 or 40 so that you get the reliable estimate of the beta, right? So let's say that's how you cluster. And once you cluster, you can get for each cluster the ratio of the target and the source OD pair, OD mode, just target and the source mode for that OD pair and that time period, all right? Now, once you have for each cluster, if you have some other OD time pair which is not there in the sample, all you need to figure out that which cluster that OD pair belongs to, that you can obtain based on some characteristic that you can create some basic understanding of how closely this OD time pair is to the each cluster, and figure out which cluster is the closest, and you can assign that value to the beta. So this is another simple way to estimate the beta more reliably and at the same time assigning the value. But there are two major issues in this. First, we are assigning the same values for the all OD pairs in that cluster for the ratio of the target and the source mode. And second is we are using the same granularity for the all OD pairs, right? But we don't need to use the same granularity for the all OD pairs. Why we are doing the clustering? We were doing clustering so that we can get the reliable estimate of the beta, right? So what we can do is we can find another way to find a reliable estimate of the beta without assuming the same granularity for everyone. So to illustrate the concept a little bit further, while the bottom line has to be clear. Bottom line is we have to estimate beta such that it's reliable. Once we have beta, we have kind of for OD time each OD time pair, we have the ratio of the target and the source mode, and then we can create the demand for the non-transit mode, right? So what we did is we created multiple granularity of the clustering, right? We said, okay, let's not worry about only one set of granularity. Let's create multiple set of granularities, and let's create the clusters for them. And rather than just assigning the same value for each clusters, for each granularity, you can develop a supervised learning process rather than assigning the same value to each granularity, right? But now the question is, for each OD time pair, which is not in the sample, how do we decide the granularity level, right? And that boils down to, why did we do the granularity at the first place? The granularity was done at this first place to get the stable estimate of the beta, because it is noisy, right? So what do we do? To decide the granularity, appropriate granularity for each OD time pair, what we do is we look at the mode share ratio estimate for the different ranges of the granularity in a specific time window. And in that time window, if the ratio of that mode share is not changing too much, if it is fairly stable, then we decide choosing that level of granularity for that OD time pair. So that helps in stabilizing the value of the beta, the ratio of the target and the source mode share. And finally, that can be used to estimate the non-transit mode share, which is target mode in this case. So let's look at how does this simple method, I call it very simple way of thinking about this problem, because we are not doing any fancy math here. We are just using the fundamental idea that how do you estimate beta, and then use that to expand the matrix of the transit OD matrix that we have. So let's first look at the data here. So if you look at that origin destination matrix, you have let's say 421 traffic analysis zones, and we are considering the 2 hours time period window here. So if you look at the unique OD time pairs in the household travel survey data, you have 37% coverage So if you look at the OD pair level, we still have a decent coverage. But as soon as you get to the OD time level coverage, you have only 13% of the OD time pairs which are observed in the household travel survey data. So you have to estimate the beta for remaining of the 87% of the OD time pairs, right? That's what it means from a practical perspective. I'll not go into these details, but we are just looking at the different type of algorithms and how they perform. I'll directly talk about how do we validate this approach, because you need the third data set to always validate. So I can tell you one thing with these emerging data sets, without the validating your approach, people don't trust how well your method is working. So we have spent a lot of energy and effort in validating our approach. And one of the validation that I'm going to show is for Seoul, but now we are able to validate for the South Korea as well, for the Singapore as well. So let's look at the cellular data set, which we haven't used in the whole process. But how does our time-dependent OD matrices that we generate actually align with the cellular data, right? Cellular trace data, which is available in in Seoul, right? So here you have on x-axis scale cellular data. Here you have the generated one. This is for the origin destination. This is the origin time, and this is the destination time. So there are 3 dimensions, origin, destination, time. We are presenting here results for combining 2 of them, origin, destination, origin time, and the destination time, right? And y-axis is the generated one, x-axis is the cellular one. The 45 lines means if everything is on 45-degree line, that means what you are generating is very aligned with the cellular data. So even if you use a very naive supervised learning method to estimate beta, right? You are able to do quite well in the origin time and the destination time OD matrices, right? In generating them. But you are not able to do so well when you are looking at the OD pair level demand. Why is that? Because the number of combinations that you have is 400 times 400 here in this one. Here you have 400 times 12, here you have around 400 times 12. So the dimensionality is the issue that here the supervised learning is not able to do so well. But if you look at the last method that I talked about, which is presented in the last row here, where we are using the adaptively selecting the granularity for the each time the OD time pair, we are able to see that not only we are able to reduce the uncertainty sort of in the origin time and destination time, the OD level flows are also able to match very well with the cellular data. Okay, so first thing, simple ideas can work if you look into the data and refine your methods. Okay, so this was quite promising to us, too good to be true, honestly, when we looked at it, because the approach is very simple in itself. And let's look at the other validations. So we look at this is from the cellular data OD matrix for the intrazonal, and this is for the generated one. And you can see all the peak areas we are able to generate quite well. So this is basically the sum of the demand for the transit and the non-transit trips. This is what we are presenting here. Because in the cellular data, you don't have the non-transit trips. So we are just using the total time-dependent OD matrix. Right? Similarly, if you look at the cellular data scaled origin time, like origin and in the morning, 8 to 10, the distribution is quite similar. And in the evening, if you look at 6 to 10 p.m., also we are able to show quite similar patterns, right? What it says is that the method is able to achieve those patterns. We are not saying that the cellular data is perfect, but thankfully I think the Seoul data is pretty good in terms of quality, because the share is around 30%, okay? So you are all being tracked, basically. Your all cell phones are being tracked very well. Okay, good. And these are some of the departure time distributions that we are able to show that are work very well. Like what you see in the red is the cellular one, and what you see in the green is the generated one, right? Good. So the main point here is that this is an approach to generate the time-dependent OD matrices, which is very useful in the areas where only transit data is available and the household travel survey data is available. And it's well validated for Singapore and Seoul. And you can look at the paper, the draft of the paper. We are still working on it. Specifically, as I was talking about epidemiology, epidemiologists are interested in mode-specific OD matrices. Why? Because the chances of infection in transit are different than chances of infection in a car or while you're walking, right? So that's why they are interested in the mode-specific OD matrices as well. So we are giving these mode-specific OD matrices to epidemiologists to see if they can do better job in modeling the disease propagation in the population. Okay, so I'll get to the second part of the first part of the lecture. But if you have any questions before that, I'm happy to take them as well. Yes.
Thank you for the interesting talk. So I just want to clarify my understanding. So you try to generate the OD metrics using the data with diverse modes. So the validation procedure you showed us is only for the smoke card data, I think, not transit data. So also the slide before, validation process you showed us is including all the modes, cars and transits and everything. Is that correct?
Yes. So validation process, I'll just repeat briefly. So we use the transit data and household travel survey data and generate the non-transit trips time-dependent OD matrices. And we already have the transit trips time-dependent OD matrices. So we sum them together. And then we look at the cellular data, which have this information, which we haven't used at all in the process. And then we try to compare our generated time-dependent OD matrices with the external data set, which is cellular data in this case. So I think your understanding is right.
Also, the other thing was there is the social demographic information in the household travel survey, and maybe software data. I think there's a partial column that you can.
I'm going to talk about the socio-demographic aspects and the other things in the second part of the talk. And we will do some validation within the smart card data, socio-demographic information, because we do have the age-related information, like older versus younger information in smart card. So we will utilize that later in the second part of the presentation. And how do you actually utilize the socio-demographic? I'm going to talk about that. Great, thanks. Any other questions? We have whole day to talk about data fusion and cognitive psychology. No? Okay, I'll go to the second topic and then we will have another round in case you get more ideas about what to talk. Okay. So now, let's say you have generated the time-dependent OD matrix using the method that I told, or maybe you got from some operator, cellular operator, you got the time-dependent OD matrices. How do you combine those time-dependent OD matrices with the household travel survey data to actually increase the diversity of the activity schedules that you generate? So that's what we are going to talk about now. To set the context, time-dependent OD matrices that you obtain from any cellular data sets or anywhere, those are privacy-preserving way of sharing the information. So those are the privacy preserving way of sharing the information by the cellular operators. So from that perspective, time-dependent OD matrices are useful. It's not the trajectory information, right? So there are less of the privacy issues. But when you are aggregating the mobility information in the time-dependent OD matrices, you're losing the connection between the trips, right? Because now you're just giving the trip level information. But those connections are well observed in the household travel survey. I wouldn't say well observed, but decently observed in the household travel survey data sets. Sociodemographics, as your friend mentioned, is also available in household travel survey data sets, right? So how do you utilize this household travel survey data information along with the rich spatio-temporal distribution that you obtain in the smart card, in the time-dependent OD matrices, right? So let's try to formalize the problem again. And the main idea is to increase the diversity, the heterogeneity of the activity schedules we generate. And when I see the results, you will see what do I mean by increasing the heterogeneity. Basically reducing this zero cell problem, going beyond the sample. Because in the sample, maybe you are observing only certain mobility patterns, but there are many mobility patterns which are missing in the household travel survey data, right? So let's try to see how do we best utilize the OD matrices and household travel survey data sets when we generate the activity schedules, right? So in principle, if you want to put this OD matrix, this problem, you have a very sparse observations of activity sequences in the household travel survey data. And you have a very comprehensive information of the time-dependent OD matrices. How do you combine them together to generate the comprehensive activity schedules? Okay. Again, here also, we will try to think from the data that we have and problem that we have, rather than just using some off-the-shelf machine learning method or some deep learning method, okay? So let's try to see how we are going to combine these things and what is a common approach to do it and how we can make it better. So let's see, what's the common approach to do it? It is not the approach which has been used in the literature, but some parts of this approach has been used in the literature. So the first idea here is, how about we use the OD matrices and convert them into the tours with the spatial and the temporal locations, timestamps, right? So this is the transitioning this OD matrix to the just the tours with the spatial location and the temporal stamps. How do we do that? Generally, we use the Markov chain type models, and I'll talk about briefly about that, how people do that. And then the second step is, once you generate these tours, you infer the demographics, trip purpose, and the travel mode using the household travel survey data distribution. Let's first try to understand formally what we are doing here, and then we try to understand what is the issue in this approach. Okay. So let's first define things more formally, like what we are trying to do in this approach. So the first variable is X, which is the sociodemographics, Y, which is the sequence of the trip chain attributes, which is trip purpose, mode choice, and the trip chain length. Z is the sequence of activity locations, S is the sequence of start time, E is the sequence of end times, and K is the trip order. And similarly, this household travel survey observations, some of them can be converted into the time-dependent OD matrix observations that you observe in the generally from the cellular operators, or using the first approach, you can create the time-dependent OD matrix. So we define the Z bar as the reason, Z tilde as a destination, T bar as a trip start time, and T tilde as a trip end time. And if you are transferring the information between two data sets, you always need to create a latent space. Why? Because one is more sparse and one is more dense. So how do you create that latent space is also very important, which we'll talk about as well. So the traditional method, how people do it, it's not that people have combined the stage 1 and stage 2 together, but I would say it's a representation of the state of the art right now, before I talk about how we are changing it right now. So if you think about what you are observing, Z, S, and E, the joint distribution of the space and time mobility pattern is what you observe in the time-dependent OD matrices, right? You are breaking this into this Markov chain type model where you have these subscripts are basically the trip numbers, right? So you are generating the next n time conditional on the sequence of the activity, conditional on the, you're finding the next n time conditional on the your sequence of the start time as well as the activity location. So based on the activity location and the start time, you are generating the n time basically. Similarly, you have this joint distribution of the location and the start time from the time dependent OD matrices that you have, right? So this is how you are keep generating, trying to decompose this spatio-temporal distribution that you observe. But what is the major issue in this? You are not using any contextual information when you are creating the tours, right? It depends on the trip purpose. It depends on the travel mode that you're using, right? But here we are not using any contextual information when we are generating the spatial and temporal timestamps. So what we are saying is there are many possible combination of the tours which can generate this joint distribution that we are observing in the OD matrix, right? But if we are not conditioning on the travel mode and the trip purpose, the distributions that you are generating for the activities or the activity instances that you are generating, they are likely to be highly unfeasible, okay? Maybe you will be generating weird activity patterns. If you combine their joint distribution, it will match with the joint distribution that you observe in the time-dependent OD matrices, but there is no real context information in there, right? And then the second step, as I told, is very easy. You figure out some conditional distribution of the demographics, travel mode, and trip purpose, and you transfer that distribution to the passively collected data by splitting the joint distribution into the two parts, right? So the major issue in this approach, overall it's an interesting idea, good idea, but the major step in the first step is it produces the many number of infeasible attribute combinations of the activities when you are just decomposing the joint distribution of the cellular OD matrices into the activity tours without considering the travel mode and trip purpose in that step, right? Okay. So what we are saying is we are taking a little bit different approach here. We said, okay, rather than first generating the tours, let's first do the fusion and that generate the tours so that we can condition on the travel mode, trip purpose, and all this when we are generating the activity schedules. Okay, so the first step is data fusion and second step is generation, okay? And the first stage of the data fusion is basically what we are doing is you have a comprehensive time dependent OD matrix from the passively collected data or the method that we used in the first part of the lecture. And you have a sparse time dependent OD matrix from the household travel survey data. But you have a very sparse, if the sparsity increases as you add the more attributes like travel mode, trip purpose, and the demographic information. For each of that, you have a time-dependent OD matrix. It might be very sparse, but you do have the time-dependent OD matrix, right? The point is, how do you combine these two informations to get a joint time-dependent OD matrix with a full information on the attributes, right? So now you're not just decomposing the spatio-temporal distribution, but you're decomposing considering the travel modes and trip purpose. So before talking about the data fusion step, I'll talk about the second step briefly, how the activity schedule generation differ in this approach. So how the activity schedule differs in this case, if you look at the first case, this was the first case. You use the start time and the location of the first trip to determine the duration, and that duration helps in finding the start time and the location of the second trip, right? But in this new approach, what we are doing is, we are not only having the Z and S, we brought the conditioning on the demographics, trip purpose, travel mode, all the information, the contextual information when you're generating the activities, because we are doing the first data fusion and then generating the activities, right? So what happens here is now you have this socio-demographics, trip chain length, travel mode 1, trip purpose 1. So these are the new addition information we add when we are decomposing this joint distribution. Remember, the earlier joint distribution just Z and S and E. But rather than doing that, we first fuse them, X, Y, Z, S, C, and we combine the fused distribution first, and then we do the generation. So now the key point is, if we are able to find a good way to generate this fused distribution, then this method can add a lot of contextual information when you're generating the trips, and the generated trips will be more feasible compared to what you observe in the traditional method. So let's go to the first step and see how do we do the data fusion. It's a bit complex from the mathematical perspective, but I'll try to give you the intuition of what exactly we are trying to do in the first step. Okay, so let's go to the first step. How we are doing with the time. What's the time right now? 3:24. Okay. So I'll be relatively quick. Maybe 10 to 15 minutes, we will take a break. Okay. So you bear with me for next 10 to 15 minutes. Okay. So I'll not talk about all the details of the problem, but I'll give you the working paper that you can go for, look to the detail, but let's just look at the foundational part of the model. So we want to fuse these sparse time-dependent OD matrices obtained from household travel survey data with very comprehensive information that you have in the cellular data-based time-dependent OD matrices. So what do we want to achieve in this process? So in the fused distribution that we want to generate, right, we know that we want to maintain the joint distribution of the cellular OD matrices that we are observing in the passively collected data sets. So this is the constraint that we put, that the joint distribution of the cellular OD matrices in the fused data should be consistent with what we are observing in the passively collected mobility data. That's a constraint, right? Now, if you are matching this joint distribution here, you cannot match all the distribution in the household travel survey data, right? You cannot do that. You have to find some middle ground that you try to minimize the distance between the distribution, the fused distribution and the household travel survey data, right? So we are trying to preserve this because we rely on this distribution more, and then we try to minimize the distance between the distributions that are observed in the household travel survey data and the fused data, right? But the point is, as we know that the spatio-temporal attributes are very sparse in the household travel survey data. So there is no point of minimizing the distance between the X, Y, and all the spatio-temporal attributes. Rather than that, we condense all those spatio-temporal attributes in that latent space C, which is the cluster that I talked about. And we say that X, which is the demographics, C, which is the travel mode, trip purpose, order of trip chains, which is important in household travel survey data set, and the spatio-temporal information at a little bit higher, like coarse level spatio-temporal information, which is condensed in C. So let's try to minimize the distance at a little bit coarse spatio-temporal granularity, but maintain the X and Y distributions as we are observing in the household travel survey data, right? So this is why we are having C here rather than the spatio-temporal information fully as we observed in the HTS data. Okay, so that's the fundamental idea why we are not using the whole S and T here, Z or T here, but we are using C here, right? So if you think about this, it's an optimization problem, and this distance measure can be anything. Here we are using the Jensen-Senen divergence, but you can use any type of divergence to measure the distance between the distributions, right? So this one is the minimizing the distance between household travel survey data and the fused distribution. This is maintaining the distribution that we are observing in the cellular data, which is the time-dependent OD matrix, and this is just because you are finding the probability mass function for each x, y, z, and t. So this is that probability mass function should be greater than equal to 0, right? The problem is it's a simple problem looking at it, but it has very high dimensionality. The number of decision variables are too many, right? So address the number of decision variables, we have to decompose this problem further, okay? So in the interest of time, I'll not go into how do we decompose this problem, but ultimately what we are able to do is we are able to decompose this joint distribution into a very simpler optimization problem. And that simpler optimization problem helps you derive some of the propositions which helps us in creating the latent space. So it helps us in defining how you do the clustering. So if you look at the proposition 2, it says that the way you do the clustering in the household travel survey data set, such that the distribution of the clusters in household travel survey data and the passively collected data set is similar, it helps in achieving not only the fused distribution to match with the passively collected data set, but it also helps in achieving that fused distribution at the cluster level matches with what you observe in the household travel survey data. So based on that complex problem, we simplify this problem, and the simplification helps us in ways that how this clustering should be done efficiently, right? I'll not go into the details, but if you want to look at the fundamentally how we thought about the clustering and the decomposing the problem, you can look at the published paper, but I'll also give the link of how we do in this case, in this problem, where you can go into the detail and look at what's the idea of the decomposing this problem further. Okay, but I can say one thing: we start from fundamental principles and then use some ideas to decompose this problem. But it's a basic probability, so you can easily understand. It's a conditional distributions and the joint distributions that we play with. Okay, so I think I would like to show some results before we close this lecture to convince you that the method works. So as I said, the value of working with passively collected data only happens when you can validate your approach. So we do 3 validation studies: Singapore, Seoul, as well as some simulated database study. In this case, I'll talk about Singapore and Seoul case study. So what do we do in the Singapore case study? We use the full household travel survey data, and we use the time-dependent OD matrix synthesized from the first approach. We fuse them together, and then we generate the in the smart card data, we have some interesting information about the origin destination patterns of the olders and adults, and we use that information to validate that how well our activity schedules that we are generating are matching with this information in the smart card data that we haven't used, right? Because in there we are not splitting the smart card data for the older and the young, and it also kind of captures the mode choice part of this fusion process. So it captured 2 parts: socio-demographic parts and the mode choice dimension of the data fusion. When we try to match how the generated activity patterns matches with what we observe in the smart card data for the older and the adult people. And the second validation is we use the full time dependent OD matrix from the cellular data, household travel survey data, fuse them together, generate activity patterns, and then we look at the activity trip purpose level joint, like the distributions that we observe in our data and the cellular data, and at the same time the age level distributions, which have not been used in the data generation process. So let's look at the first one. And these are all validation in the simulated data. But before getting to the first point, what we are really achieving in this process, and I just wanted to mention that fact here, if you look at the unique location time combinations that you observe in household travel survey data, those are around 20,000, right? But the number of combinations that you generate are around 2.7 million, right? So you are generating 140 times more diverse population by fusing these data sets, right? So it's the heterogeneity of the population. And why is heterogeneity important? Heterogeneity is fundamentally important because if you are planning any society, right, then you will have many groups which are not present in the household travel survey data, right? Their mobility pattern will be overlooked. So you have to capture that heterogeneity which exists in the population to be able to do a better planning. So heterogeneity is fairly important if you really want to create the equitable planning in the society, right? And if you look at these numbers for the soul, it's even higher in terms of the heterogeneity that increases in this process. So I'll show you some results for the Singapore case study validation. So what you see, these yellow dots are from the household travel survey data, and the greenish dot is the generated one. On the x-axis is the generated one. On the y-axis is the smart card data adults pattern that we observe, and this is the distribution for the adults and the senior. And what you see is the generated ones are quite aligned with what we observe in the smart card data for the adults and the olders compared to what you just observe in the household travel survey data. One more thing that you can see from here, household travel survey data is very wide, but still it's somewhat on the 45-degree line. What it tells you about, it tells you that the household travel survey data is also very well collected, right? Its sampling is also very well done, that when you are just putting the transit patterns of the older and the younger people in the household travel survey data and smart card data, it's aligned, right? So this is another way to validate how good your household travel survey data is, right? So, but the generated one is very tightened in terms of aligned with what the transit patterns are for the adults and youngers. I'll skip this. And now if you look at the soul study validation, we look at the home and work distributions, and again, the household travel survey data of soul is also very good. It is very well aligned with the distributions that you observe, but the generated one is very tightened on the 45-degree line, even much more tightened compared to what you have in the household travel survey data. Similarly, the age patterns, but I think spatial distributions are even more interesting. So if you look at this one is the generated one, and this is the home, work, and the others that are available in the cellular in the cellular data, and this is the generated one. And you can see all these peak areas we are able to generate through this fusion, right? And this is the age level distribution, which is fairly different across age groups, but our generated data is also able to capture those heterogeneities that we have. So the bottom line here is there is a potential to fuse these data sets, and if you think about the problem more fundamentally in terms of what are the things that you want to achieve, you can formulate the problem, and then you have to just find a way to simplify it further. And I would say that in all the passively collected data research, validation is the most important thing. If you're not able to validate it, then no one will believe whatever you're doing, okay? So in all the papers that we are submitting to good journals, it's difficult to convince reviewers if you don't really show the validation. So it's not just having 2 data sets, you have to have 3 or 4 data sets to be able to show that, okay, there are some parts that we are generating, fusing them, and then you are able to compare. There is one more big issue is about the biases in these data sets, because there is always this self-selection issue that some people might use the one cellular phone company more than the another. So these are these kind of biases as well, but on an aggregate level, you can see that it all works out quite well if you do things well. So you can find the paper here, and these slides will be circulated to you as well. So I think you can look into the mathematical details of the first step of the data fusion. Okay, so what's the time now? Now the time is 3:37. So maybe we can come back at 3:50, and then I'll try to wrap up in 45 minutes. Okay, great. So, but in the meantime, in 13 minutes, you can come to me and ask questions as well. So I will be around. Okay, thanks. Let's come back at 3:50.